Okay, we'll get started today. You guys can hear me? All right, it's like, can anybody in the back hear me? No? All right, hello everybody. We're going to get started today. It usually works best when one person's talking. Hello, can you guys hear me? Come on. I don't know if the mic is working today or not. Just a little bit. All right. I don't know if there's a microphone control here or not. I cannot find one. I'll have to ask about that. Oh, shit. Try something here. Shit, come on. See if that works? No? Okay. I will talk as loud as I can since I don't know if my microphone is working so well today. So we're going to get started with today's class, and thank you. Okay, so I do have a couple of little announcements today. These are both, I think they're the same thing. I've been getting contacted by many different offices on campus at the beginning of the semester about tutoring opportunities, and I think these two are the same, but I put them both in there because I wasn't sure. So anyway, what we have here are opportunities from Launch, and specifically the group tutoring that they're advertising here. Launch is the main tutoring center on campus. All other services are free, and they have individual and group options. This used to be called Chem Gym, but I think they're just making it more generic and calling it group tutoring now because it's offered for a lot of other classes as well. They have a schedule here, some information that you can look into. And I think we'll talk a lot about this throughout the semester, the different work habits and things that are necessary to do well in this class. And I think going to a regularly scheduled group tutoring is a very good thing to do. It builds sort of that regular study habits, allows you to get some help and extra practice. So I will certainly encourage that. And again, there's two slides about this, but I think they're both the same thing. So you can check out the links and see. All right, today we're going to continue on with where we left off last time, talking now in more detail about the structure of the atom. But first, the other announcement I have is that there's no office hours today. This will not be a regular occurrence that I cancel office hours, but just once in a while, and this happens to be one of them. But anyway, getting into the material, last time we ended with the idea that all substances are made up of atoms. Elements are made up of a single type of atom, and compounds would be more than one atom combined together in some way, which we'll learn more about later. And then that kind of leads to the question of what really are atoms themselves made of? Are they just the world's tiniest marbles, little nondescript spheres of matter, or is there more to it than that? And so scientists began studying that, and one of the key experiments that started leading to some better ideas about what atoms are made out of is this cathode ray experiment. So I'll describe it here briefly. This was done by J.J. Thomson as the scientist. Again, sometimes we'll ask you to be familiar with some of the key names, really only in this first chapter or two. Beyond that, it's not really going to come up as much. But anyway, the way the cathode ray experiment worked was the cathode here is just a piece of metal, and you apply a high voltage to it. And he noticed that there was a beam coming off of that metal when the high voltage was applied. He directed it through an electric field, that's what these little red coils are here, and noticed that it was repelled by the negative pole of that electric field. So he then concluded that that ray was negatively charged. So let's look at then what these key observations are. You generate these cathode rays with a really high voltage, and it was noted that they are repelled by the negative side or the negative pole of the electric field. So that was the key observation. The other thing that's important about this is, as I said, the cathode here is a piece of metal, and it's not just that one type of metal works. He tested a bunch of different materials, a bunch of different metals, and they all produce these, what are now called electrons. So these electrons that were generated, which are what made up the cathode ray, those could be produced from many different materials. So it seemed to be that, in general, everything, every substance that he tried had these electrons in it. So then he concluded that everything has electrons. And so then the conclusion was that all atoms contain electrons, and this is still believed to be true today. And the other thing that he could determine from this experiment, which is a little bit of quantitative, we talk about qualitative, quantitative observations. So there was one quantitative observation that came out of this. In addition to just showing that electrons existed, what he also found was that you could determine numerically the charge to mass ratio of the electron. He couldn't, with this experiment, you can't determine individually the charge of an electron or the mass of an electron, but you can determine the ratio of those two with this. And again, the key thing being that they're negatively charged. So that was the first experiment that led to the idea that there are electrons in atoms. And then the second one that gave us even more insight and gave us more quantitative information about them is the oil drop experiment. So this was done by Robert Millikan. So I'll show you some of the photographs of these. You'll notice that they all look kind of bitter and angry. I mean, if a general chemistry class 100 years from now was talking about my scientific discoveries, I think I'd be pretty stoked, but these guys can't even crack a half smile about it. But anyway, what Millikan did was an experiment that really just relies on pretty simple physics. So he generated like an aerosol, basically, or a really fine spray of oil drops, and he had an electric field in there that would ionize those. So basically that would add electrons to them, kind of like static electricity, essentially. So putting static electricity into these drops. And then he watched them fall against an opposed electric field. So basically, if you guys have taken physics before, free body diagrams, stuff like that, the gravity is pulling the drops down, the electric field is pushing them up, and when you set the electric field to balance the force of gravity, those drops are suspended. And so then from that, he can back out what the charge is of an electron, because the amount of force from the electric field depends on the charge that it's interacting with. So there's a lot of physics there that we don't need to know the details of, but we'll give, again, the key qualitative observations. So the falling negatively charged oil drops were stopped by an electric field. So the oil drops were, again, given a negative charge, and then they were dropped into an opposing electric field. And when the opposing electric field equals the force of gravity on those drops, they would be arrested in the air. Now, the other thing that he noticed is that, not every drop has the same charge. So some drops get more charge than others, but the magnitude of that charge occurs in regular increments. It wasn't a continuous value that he could get for the charge. It was 1 unit, 2 units, 3 units, whatever that fundamental charge unit is that he was measuring. They always occurred in those regular intervals. It wasn't continuous. You couldn't have anything in between those sort of discrete values. And so that was another important information that led him to believe then that the charges, these electrons, are discrete particles. In other words, an oil drop can have 1 electron or 2 electrons in it, but it can't have 1.3 electrons or 1.8 electrons. It has to have a whole number of these fundamental particles in it to produce that charge. So the charges on the oil drops always occur in regular whole number intervals. And the other thing that this experiment determined, I'll give you the numbers in a little bit, although you certainly don't need to memorize them, but you'll want to have a little bit of an idea of the context of them, he determined both the mass and the charge of the electrons. So the previous experiment gave you the mass to charge ratio. With this experiment, more quantitative in nature, he could determine both of them, the mass and the charge. And as you'll see, they're both exceedingly tiny, but nonetheless, this experiment showed that they occur in regular intervals, and that each electron is a discrete particle. You can't have a partial electron, you can't have a partial charge in between the charge of one electron. It always occurs in those intervals. So having demonstrated that there was negatively charged electrons as part of atoms, of course it follows logically that there has to be positive charge in there as well. The atoms themselves are charge neutral. There is no net negative or positive charge in an atom, so there has to be positive charge to balance it. And so the first idea about what this looks like is called the plum pudding model. So plum pudding is a dessert that looks like this. I guess it's popular in the UK. It doesn't look like pudding to me at all, at least what I would call pudding, but that's what it's named. But anyway, the model was come up by Thomson, the same Thomson that came up with the cathode ray experiment. And so what he proposed was you have these discrete electrons, and that would represent the raisins or the plums, I guess, in this plum pudding, and they're kind of just floating around in a diffuse positive charge. So the positive charge is kind of just like a mesh, diffuse mesh that these electrons float around in. That was called the plum pudding model. Now, a model is kind of like a theory. We introduced the term theory last time. Model and theory kind of mean the same thing. It was a proposed explanation for the structure of an atom. Again, knowing that there's negative charges, knowing that there's positive charges, this was a proposal for how those two charges are arranged in the atom. So it says that atoms consist of electrons, which of course we know from those previous two experiments that I described, and the electrons are held in place by this diffuse cloud of positive charge. Right, the electrons represent the raisins or the plums in the pudding, and the positive charge is I guess what you call the cake or the bread that holds it together. So there's a diffuse cloud of positive charge. So the electrons are randomly embedded in this. There's no real regular path or motion of the electrons. There's no regular arrangement of them. They're just sort of randomly embedded and floating around in that positive charge. So, as we talked about last time with the scientific method, if you have a model which is sort of related to a hypothesis or a theory, some explanation for a physical phenomenon, what you have to do then in the scientific method is test that model out. And so that led to an experiment to test out the... Crap, if I touch this thing, it goes off. I'm sorry. All right, so that led to an experiment to test whether this plum pudding model was actually correct or not, and it was called the gold foil experiment. So again, the name associated with this is Rutherford. We're getting close to the end of the names. Don't worry, they're not going to be on every slide throughout the semester. Just at the beginning, we introduced a lot of them. So Rutherford did the gold foil experiment. And so what the gold foil experiment involved were alpha particles. We're not going to really introduce exactly what alpha particles are in this class. Very end of Chem 2, you might see it. But alpha particles are basically heavy, positively charged particles. That's really all you need to know about it for now. So there's these heavy, positively charged particles, and he blasted them into a thin piece of gold foil. So that's what this is showing down here. You have an alpha particle generator, which again is sort of nuclear chemistry, kind of far out stuff. But these alpha particles go in as a beam moving very fast, and they hit a thin piece of gold foil. Okay, so the expected outcome of this, if the plum pudding model was correct, is that because the positive charge in the atom is very diffuse and these particles are positively charged, most of the alpha particles would just pass straight through if that was the case. It's kind of like, shooting a BB gun at this piece of foil. You guys know if you shoot a BB gun at a piece of foil, they're going to just go right through. And that's kind of what they thought would happen if all the charge was just really diffuse and not very dense. So the expected outcome, the hypothesis of this experiment with the plum pudding model as the backdrop, is that these alpha particles would mostly pass through. Or maybe because, you know, there is that positive charge in there, they might be deflected a little bit. It wouldn't be impossible for them to have a slight deflection in their path because of the positive interaction. I guess a key concept in chemistry that you're probably familiar with, physics as well, I suppose it spans both of them. If you have two charges that are alike, they repel each other. So again, you're having these positively charged particles coming into the atoms that themselves have positive charge, but most of them will just pass right through because that positive charge is really diffuse. Some might be deflected a little bit, but again, there was not an expectation that much would happen. Now the actual outcome though, which is illustrated in the picture down here, is that while it is true that most of the alpha particles pass straight through, some of them get deflected at pretty severe angles, sometimes even coming like straight back to where they came from, basically, you know, almost like they're bouncing off a wall. So a small portion of the alpha particles were deflected pretty severely. So most passed straight through. That was still the case. So if you weren't looking closely at this, you might think that the hypothesis was correct, but you did notice that some of them were deflected pretty severely. So some were deflected at very large angles, even coming straight back to the source in some cases. So deflected at large angles or even reflected completely back to the source. And there's no real way to rationalize that with the idea that the positive charge in an atom is this really diffuse, ill-defined cloud. So the only explanation for this is that the positive charge and most of the atom's mass are in a very small, very dense region. So a very small area, which they then call the nucleus. All right, so long story short, the gold foil experiment demonstrated the existence of a nucleus, which is the idea now that instead of having a diffuse cloud of positive charge, you have this really dense region at the center of the atom. That's your nucleus. That's where all the positive charges, and then around that, you have a diffuse cloud of electrons. And chapter 3 is all about how that electron cloud behaves, or mostly about that. So we'll get to that a little bit later. Some of it in chapter 2 as well. But the idea is that you have really dense nucleus at the center, diffuse electron cloud. Most of the atom is actually empty space, and that's why most of the alpha particles still pass through, because there's a lot of empty space in atoms. Very, very tiny region of positive charge. Electrons floating around all over that, and a lot of empty space in between. Okay, so it's a diffuse electron cloud surrounding this nucleus at the center. So again, another key insight from this is that atoms are mostly empty space. All right, so those are the ideas that came out of the gold foil experiment demonstrating the existence of a nucleus. Okay, so from there then, that leads to the following summary of all of what are called the subatomic particles, the little tiny particles that make up all of the atoms that we have. All right, so we know that there has to be positive charge, as we demonstrated from that experiment. So those are called protons, abbreviated sometimes as P+. Their relative charge is +1. And their absolute charge in the unit of coulombs, which is the standard SI unit for charge, very small number. Each proton has a very tiny amount of charge, but it's 1.60 times 10 to the minus 19. And then the relative mass of them, so we're going to talk about both the relative charge and the relative mass of all these different particles. Relative mass of a proton, we'll set that to about 1. And then the absolute mass in grams, again, a very tiny number, so tiny that's hard to even comprehend in human scale. but it's 1.67 times 10 to the minus 24. Okay, now the other thing that was discovered later on, and we're not going to go through how it was discovered because it's pretty far out, pretty modern physics, so it's not something that we need to cover in this class, is that the nucleus, we said, has all the positive charge and most of the mass. It was found later on, really not until I think probably 100 years ago or less, well after these discoveries were made, that the nucleus also contains neutrons, another subatomic particle. So again, those were discovered later on, and the experiments that they used to discover those were pretty complex, I would say, so we're not going to cover them in this class. But nonetheless, you have these neutrons as well in the nucleus. They would be abbreviated as N0. Now, the thing about a neutron is that it has no charge. So all the positive charges in the protons, all the negative charges in the electrons, but there are also some charged neutral particles called neutrons that are present in the nucleus as well. So their relative charge and their absolute charge are both 0. They have no charge. But their mass is about the same as a proton. Now I'm putting this little approximately sign here because they're not exactly the same, but they're close enough to within, several digits that we don't need to worry about the difference between them. So their mass also to 3 significant figures is exactly the same, 1.67 times 10 to the minus 24 grams, or in a relative sense they're 1 to 1. They have the same mass. And then we talked about the electrons being the negative charge. That's the first one we introduced. So their relative charge is -1. They have exactly the same magnitude of charge as a proton, but just opposite in sign. So there's no difference in the size of the charge, just the sign. So it's just minus 1.60 times 10 to the minus 19 coulombs. Same number as proton, just opposite in sign. But the big difference between electrons and the other two is the mass is way, way smaller. So the relative mass of an electron, if these are set to 1, is 0.000549. And in grams, that's going to be 9.11 times 10 to the minus 28. So these are, 10 to the minus 24. This is less than 10 to the minus 27. So it's about 1,800 times smaller if we want to do it in sort of relative terms. So the mass of an electron is about 1,800 times smaller than the mass of a proton or a neutron. So essentially, to the level of precision that we care about it, all of the mass in an atom is in the nucleus, the protons and the neutrons. The mass of the electrons don't really matter in terms of determining what the overall mass of that atom would be, because the electrons are exceptionally tiny in terms of their mass. They have significant charge, negative charge, that's exactly the same in magnitude as the proton, but their mass is exceptionally tiny. So those are all of the subatomic particles that make up an atom. And the other thing that's important about these then is that the number of each subatomic particle that you have determines the identity of the atom. So we talked last time how part of the atomic theory was that atoms from different elements are, so if you have an atom from a given element, they're all identical and they're distinct from other elements in terms of their mass and other properties. And it turns out at a more detailed level, what distinguishes one atom from another that would make up one element from a different element is the subatomic particles that they have. How many protons, how many electrons, how many neutrons they have. So that's how we're going to then define what distinguishes one element from another in terms of the structure of their atom, is how many of each of those they have. So what really, at a fundamental level, distinguishes one element from another, what distinguishes hydrogen from helium, from lithium, from beryllium, from boron, from all the other ones, carbon, nitrogen, oxygen, fluorine, if you go through the periodic table that you have over there, what distinguishes them from each other is the number of protons in the nucleus. So every hydrogen atom will have the same number of protons in the nucleus as every other hydrogen atom. Every carbon atom will have the same numbers of protons in its nucleus as every other carbon atom. So that's what helps you, that's what allows you to tell one atom apart from another in terms of the element that they compose. And so the way we kind of abbreviate this then is with an atomic symbol. So there's 3 parts to an atomic symbol, and I'll color code them and define them separately. So let me just write it out first. Okay, so there's those 3 things that are different in terms of their symbol, and I color coded them in case you like that. All right, so this main part here, X, is the atomic symbol. So it identifies, or helps you identify anyway, what element you're talking about. So it's a 1 or 2 letter abbreviation. For the element that atom represents. just by convention, so you're aware, the first letter is always capitalized. So if it's a one-letter symbol, it's a capital letter. If it's a two-letter symbol, the first letter is capitalized, second letter is lowercase. Okay, so that's what X represents in this generic atomic symbol. Now the other one here at the bottom, so in addition to the symbol X, which is a letter or two letters, you have two numbers that are associated with that as well. So A and Z are both numbers. Z, the one at the bottom, is called the atomic number. And that number gives you the number of protons in the nucleus. Now, as we'll see later on, Z, the atomic number, is not always included in the symbol. And that's because the number of protons in the nucleus identifies what the element is. So you don't need to have the symbol and the Z. They both kind of tell you the same thing. They tell you what element it is in different ways. So a lot of times you'll just leave out Z altogether in atomic symbols, and you'll just have the other number A along with the symbol X. And so sometimes Z is not even there. So we'll get to that a little bit more later on. All right, and then the last number, though, A, which you do need to use when you're talking about an individual atom and trying to define it, is called the mass number. And this is going to be the number of protons plus the number of neutrons. So P plus for protons plus the number of neutrons, and 0. So it's the combined number of protons and neutrons that you have in the nucleus of that atom. Okay? So that's what the mass number represents, A. All right, so those are going to be the three things that make up an atomic symbol. And what atomic symbols allow you to do, or one thing they allow you to do, is to distinguish what are called isotopes. All right, and isotopes kind of gets us to really the one part of the atomic theory that's wrong. So last time we introduced Dalton's atomic theory, which is sort of the explanation for all the mass laws and the basic ideas about how substances are made up of atoms and how atoms are all different from each other and different elements and blah, blah, blah. But one thing they are wrong about is the atomic theory says that all atoms of a given element have the same mass as each other. And that's not entirely true, because in many cases you have what are called isotopes, which are atoms of the same element, but they have different masses from each other. And the way that they have different masses is that they have different numbers of neutrons. So let's define what an isotope is first. They're atoms of a given element. So we're talking about a single element here. And we'll give an example below for hydrogen of how this works. So atoms of a given element that differ in the number of neutrons. And because they have different numbers of neutrons, that means their mass numbers are also different. That differ in the number of neutrons. And because they have different numbers of neutrons, they have different mass numbers or different masses. All right, and so just to rub salt in the wound a little bit, that means Dalton was wrong about this, because his supposition in the atomic theory, as I mentioned, was that all atoms of a given element have exactly the same mass, but in reality that's not true. There can be atoms from the same element that have different masses from each other because they're what are called isotopes. Not all elements have multiple isotopes, but many of them do. Most of them do. Now the thing is, though, when you have isotopes, the properties of isotopes for a given element are nearly identical, except for their mass, of course. So if you talk about their chemical properties, how they react with other atoms and other substances and their kind of chemical behaviors, their other physical properties like melting point, boiling point, blah, 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 that we'll learn about later on in the course, all the other properties except for mass are basically the same for different isotopes. So the properties of isotopes for a given element are nearly identical. The properties are mainly determined by the identity of the element itself, not which isotope you're talking about. So it doesn't really change things too much when you have multiple isotopes. Although there can be some important differences, not something that you'll see a lot in this course, but it comes up sometimes in biochemistry or other fields where different isotopes can sometimes behave a little bit different from each other, and that can have an effect sometimes. All right, so here's some examples of isotopes. So if we have hydrogen, the simplest atom on the in the world on the periodic table. All right, so here's the abbreviation for hydrogen is H, and if we go and look at the atomic symbol, Z for hydrogen, the number of protons in the nucleus is 1. It's the smallest atom you can have. It has just one single proton in the nucleus. So the number 1 would go down here if you were doing the full symbol. And then one of the isotopes of hydrogen, the most abundant one as it turns out, the one that makes up most of the hydrogen that's on Earth, has 0 neutrons in the nucleus. So it just has a proton, no neutrons at all, and so that means the mass number is also 1, because the sum of the protons plus neutrons, 1 plus 0, is still 1. So this is the most abundant isotope of hydrogen, and it has 1 proton in the nucleus and 0 neutrons. Now there are 2 other isotopes of hydrogen that can occur. One of them occurs naturally, one of them is radioactive, so you don't really see it too much, but it can be prepared. But the one that does occur naturally, in small amounts anyway, is hydrogen 2. So the only difference here is that it still has 1 proton because it's still hydrogen, so that atomic number Z is still 1. You're not going to change that if you're talking about the same element. But now we have a mass number of 2 because this isotope has 1 neutron in the nucleus instead of 0. So the only thing that differs between isotopes is the number of neutrons, as we said. And this one is called deuterium. It does have a separate name. Most isotopes don't have separate names, but for hydrogen they do. So hydrogen, deuterium are slightly different names, but you guys don't need to know that. It does have significance biologically, though, or it can, because if you make water out of deuterium, so if you have water, but instead of having hydrogen 1, it has hydrogen 2 in it, or alcohol, I suppose, as well, if you're into that type of beverage. But anyway, if you have hydrogen 2 instead of hydrogen 1 in water or any other beverage, your body metabolizes it significantly slower, and if you drink too much of it, that can lead to fatal consequences. So I'm not going to teach you too many times how to off other people, but that's one way, is to give them deuterated water. They wouldn't even be able to tell the difference. It looks like water, tastes like water, still the same color, everything else, but the body would metabolize it so much slower, and it would slow down your metabolism. Or you don't really metabolize water, but water's involved in metabolism. It would slow down your metabolic processes, and if you have too much of it in you, that can be really bad. So this is one situation where isotopes are significant, in part because these 2 different isotopes of hydrogen, the mass is different by a factor of 2 because they're so small. So hydrogen 1 has a mass number of 1, hydrogen 2 has a mass number of 2, so basically this isotope is twice as massive as the other one. For most other elements that are heavier, if you just change 1 neutron, you're not really changing the mass by very much in a relative sense, so it doesn't matter as much, but for hydrogen it does. So that's an aside, but anyway, the third isotope of hydrogen, which is radioactive, is hydrogen 3, also called tritium. Still 1 proton, it's still hydrogen, but now we have 2 neutrons in the nucleus. Okay? So those are the 3 isotopes of hydrogen. There's not an easy way to predict how many isotopes each element will have. That's not something you guys have to worry about, but the fact of the matter is most elements have multiple isotopes that you can observe, and that only differ with respect to the number of neutrons that they each have. Okay, so that's going to be how we define isotopes. Any questions up until this point? Should probably pause here and there. All right, so let's just do a few typical types of sample problems that you guys would have. Not too different from homework problems. So let's say we have the 2 most abundant isotopes of palladium, which has the symbol PD. Palladium is commonly used in jewelry. It's also used in catalytic converters in cars, so it's out there. And so these are the symbols for the 2 most abundant isotopes. We want to know the number of protons, electrons, and neutrons that they each have. So with the full atomic symbol given to you, it's usually pretty straightforward to get this, because again, this bottom number here, which is called the atomic number, directly gives you the number of protons. So we don't have to put any thought into that one. If the number is given to you directly, then you just copy it down. That's the number of protons. No big sweat there. Now the one that takes a little bit more effort, but I think we can all add and subtract in this room, is to find the number of neutrons, because here, this number here, the mass number, doesn't directly give that to you. It gives you the protons plus neutrons. So we have to do a little bit of subtraction. So the number of neutrons that we would have is going to be the mass number, which is 106, minus the number of protons, which is 46. So again, the sum of protons and neutrons equals that number. So 106 minus 46 is 60. So this isotope has 60 neutrons in the nucleus. Now the last one, which is the number of electrons, we actually haven't talked about it yet, But for a neutral atom, that is also exceedingly simple, because a neutral atom has no positive or negative charge, meaning that the number of electrons that you have has to totally balance out the number of protons that you have. So in this atom, we already found that there's 46 protons. Because there's no charge, there also has to be 46 electrons. So the number of electrons has to equal the number of protons in a neutral atom. So that will also be 46. We're going to talk about ions in a little bit, so that won't always be true, but if it's neutral, if there's no indicated charge in the atom, there has to be the same number of protons and electrons so that the positive and the negative charges cancel each other out, add up to 0. Okay, so that's the first isotope. The second one for palladium, 108 is the mass number now. So because we're talking about the same element, and because we gave you already directly the atomic number, this one will have the same number of protons and electrons as the first one, and so still 46. So protons and electrons are both still 46. It's still the same element, palladium, and we, again, directly gave you the atomic number right there to directly tell you that. Still uncharged. The only thing that changes when you have a different isotope, as we've already said multiple times, is the number of neutrons. So this time the mass number is 108. The atomic number is still 46. That didn't change. But that leaves us now with 62 neutrons. So the only difference between these two isotopes is the first one has 60 neutrons, the second one has 62. But that would distinguish them as isotopes. Okay? Any questions on that? Okay, we're doing okay on time, I think. All right, on to the next one here. This one asks you to produce the symbol. Obviously, in Blackboard, you can't write complicated symbols like this, but it might be a part of a multiple choice question or something of that sort. So you should still know how to do it. So we have a fictitious element with symbol Q. If you look at the periodic table, you won't find a real element that has the symbol Q. This is fake. And it has 34 protons and 43 neutrons in the nucleus. We want to write the proper atomic symbol for this element. So this is just kind of working backwards from the previous problem. We gave you the symbol last time, asked for the number of subatomic particles. Here we're doing the opposite. So if we remember, as we just learned, the atomic symbol has 3 parts to it. A letter symbol that identifies the element, the atomic number, and the mass number. All right. Now the atomic symbol is we're already told that that's Q, so we already have that part of it. And that again just identifies which element it is, this time a fake one. But to find the bottom number here, Z, remember that directly tells you the number of protons. So we just search through the problem and find that we're told that it has 34. So that's going to be the bottom number, Z. The mass number, A, is the sum of protons and neutrons. So we had 34 protons. The problem directly tells us that there's 43 neutrons. So those two added together, 34 plus 43, fairly simple math, is 77. So that's going to be the upper number there, A. So that leads to this being the final symbol. Q is the atomic symbol. The atomic number is 34. The mass number is 77, and they go together like that. Okay? So you should be able to work in both directions, because there could, again, be at least multiple choice questions that ask you to identify symbols properly. But it's the same concept either way. All right. Now, the other thing that we can do is, as I kind of already mentioned briefly, the atomic symbol doesn't always include the atomic number, because it's kind of redundant. You know, the atomic number identifies what the element is. Each element has a unique atomic number, but then the symbol that's in there also tells you what the element is. You don't really need both of them necessarily. So you can use the periodic table of elements to find the number of protons. We're going to go through the periodic table of elements in a lot more detail in, I always forget which happens in chapter 2 and chapter 3, but one of those 2 chapters will have a lot of information about the periodic table, probably chapter 3, I think. But we'll talk about the basics right now, which is that if you look at an entry on the periodic table, they sometimes are formatted differently from each other. There's one over there. The one that you should become familiar with is the one that we give you on your exams, which I think is put at the beginning of every homework assignment, but if not, it's in Blackboard. You can find it there. So make sure you're familiar with that periodic table. It looks very similar to this. I think the only difference is that our periodic table doesn't actually name the element, but the rest of it's all the same. But anyway, if you look at an entry on the periodic table like this one for carbon, this whole number that's at the top directly tells you the atomic number. And then each one is unique for every element. And so if you look at the periodic table at some point, which you will eventually if you haven't already, you'll notice that all the elements are arranged in that numerical order. 1, 2, 3, 4, 5, 6. That's the different atomic numbers that each of them has, the different numbers of protons that they each have in their nucleus. So that's the atomic number. This number down here we don't really need to worry about too much right now, but it is related to the mass number. But it's not exactly, as you can see, it's not a whole number, so it's not exactly a mass number. We'll define that later on, but it is related to that if you were wondering. So this will be covered much later, probably not until like chapter 4, I think, what that number actually means. But it's related to mass number, which we have already defined. All right, so to sort of bring this home then, as I've mentioned now at least twice, Z, which is the atomic number, is usually left out of atomic symbols. I've been drawing atomic symbols so far that include it, and you certainly may see that in some of the assignments, but in a lot of atomic symbols, the atomic number Z is left out. So if we were writing the full atomic symbol for the isotope of carbon that has a mass number of 12, which is also its most abundant isotope, we would have the symbol C, and as we said, we can include the atomic number there, 6, which is, again, directly from the periodic table if that's where you're looking, and then if we said the mass number is 12, that would go up here. So that would be the full atomic symbol, and that is certainly correct, but in many cases, you'll only see the mass number given here, so it'll just be written as 12C. So that's the more common way of writing the isotope symbol or the atomic symbol for carbon-12 isotope. Okay, so this, as I said, is more common. And that's because the atomic number Z is redundant with the symbol. You will never have an atomic symbol of carbon where Z is not equal to 6. Z is always equal to 6 for carbon because, as we said, the atomic number Z defines that element. Each element has a unique atomic number. So you could put the 6 there, but it will never not be 6, so there's really no reason to have it both. Especially if you have a periodic table in front of you, even if you only have the symbol for carbon C, you can quickly look at that and find what the atomic number is being 6. So you don't need to have both of them indicated in the symbol. So just be aware of that. The atomic number is, in many cases, probably more cases than not going to be given to you in the atomic symbol. All right, the last thing we're going to talk about with respect to atomic symbols is what happens when we have ions. So let's talk a little about what ions are. So ions are going to be where we take an atom and we either remove or add electrons from it. So we either remove some of its electrons to give it a positive charge, or we add some extra electrons to it to make it a negative charge. We'll see a lot more about ions later on, so we're just going to give the real basics now about how we talk about how many protons, neutrons, and electrons they have. So as we've already said, if you have a neutral atom, one that has no charge, they contain equal numbers of protons and electrons. Okay. Now, when you form ions, the way that you will always do it is you're going to remove or add electrons. We never change the number of protons in the nucleus when we form an ion. First of all, that would change the identity of the atom altogether. It also turns out that that's exceptionally difficult to do. You're not going to have a chemical reaction where the number of protons changes. So in chemistry, when you're talking about, forming ions or doing any sort of chemical reaction involving atoms, electrons, not elements. So you're going to remove or add electrons to form ions. All of chemistry, all of the action in chemistry involves the electrons. It's not that the protons and the neutrons aren't important. They're in the nucleus, they define what the element is. But when you're talking about chemical reactions or forming ions, it's always going to involve electrons only. So that's how we form ions. We just either remove some of the electrons, add additional electrons, and that gives the atom a net charge. Okay, so to just reiterate, you never want to remove or add protons when you're talking about forming an ion. Because if you do that, that changes the identity of the atom. It's no longer an ion, it's a totally different element altogether. All right, an ion is just an atom that has either not enough or some extra electrons. And in terms of then how that affects the number of subatomic particles, when you form an ion, you don't do anything to the nucleus. So the number of protons stays the same, the number of neutrons stays the same, but you just add one electron for each negative charge. So if you have a -1 charge, that means you have one extra electron. If you have a -2 charge, you have 2 extra electrons, and so on. And then you can also have positively charged ions where you subtract 1 electron for each positive charge. So a ion with a +1 charge would have 1 fewer electron than the neutral atom. An ion with a +2 charge would have 2 fewer electrons, and so on. So it's always just about changing the number of electrons when you talk about how many subatomic particles an ion would have. Okay, so let's give 2 quick examples. One is pretty straightforward, one's a little bit more complicated. So here we have, this time, it looks like an atomic symbol, but it has an additional number up there. So if you see a number in the top right, which is usually going to have either a plus or a minus sign next to it as well, that tells you what the charge is. So if there's nothing there, it's neutral, but if you see a 3+, that means there's a +3 charge. If you see a 3- or a -3, that means there's a -3 charge. So whenever you see that extra number up in the top right, that tells you that you're dealing with an ion. So we want to know how many protons, neutrons, and electrons are present in the following ion. This symbol here, IR, is for the element iridium, and to see who actually pays attention in my class, I'll mention multiple times throughout the course that iridium is my favorite element. So if you remember that by the end of the course, that means you've been paying attention at least a little bit. So anyway, you should all have your own favorite element. If you don't have one yet, you will by the end of the course, I promise. You'll be as cool as I am someday. Okay, so anyway, iridium has this symbol here, and we want to know number of protons, number of neutrons, number of electrons, but this time it's an ion because it has a +3 charge. So the number of protons is still defined by the atomic number, which here is directly given to you. If it wasn't, we would look up IR on the periodic table and find that its atomic number is 77. For the number of neutrons, we also do it the same way as before. We just use the mass number here. So the number of protons plus the number of neutrons equals the mass number, which is 192, which means that the number of neutrons is the difference between those two, 192 minus the number of protons, which is 77. And so that difference is 115. All right, so this isotope, this atom has 115 neutrons. Now the last part is the number of electrons. If it was a neutral atom, the number of electrons would equal the number of protons, and it would be really easy and would be done. But here we have a +3 charge, which means that we have 3 fewer electrons. We're deficient by 3 electrons. So instead of having 77 electrons, we take away 3 of them to give us a +3 charge, and so it's actually going to be 74. Okay, so in this ion here, you have 74 electrons, 77 protons. So you have 3 more protons than electrons, which is why you have a +3 charge. Whenever you have an imbalance between protons and electrons, that's going to lead to a net positive or net negative charge. Here there's more protons than electrons, so the charge is positive, as indicated in that symbol there. Okay, so any questions on that one? That takes it a little bit of a step further, but it's just one additional thing to get a number of electrons involved when you have ions. Okay, and then the last one here is a little bit more complex. I'm going to need to pull up the periodic table for this one. So So, because we need that to determine this. I should have done that. Let's see. Do I have the periodic table on this desktop somewhere? Yeah. Oh, that's probably the wrong one, but I guess it'll work. All right. Well, this is the one that you guys will actually use. It's just this is a larger packet that we don't need. But this is the periodic table that you guys will use, so we can start becoming familiar with it. So we'll need it for this problem here. I'll flip back and forth. I don't need comments. Okay. All right, so here let's look at this question here. Determine which +2 ion, 2+ ion, has the same number of electrons as Br-. So here we didn't even really give you anything about the mass number, so we don't even care about the number of neutrons in this problem. We're just looking at number of electrons. Okay, so for Br-, we have to figure out first how many electrons that has. That's one where we know the identity of the element and we know the charge, so we can get that. All right, so to find the number of protons in Br-, we have to go to the periodic table and figure out what the atomic number is for bromine, which has the symbol Br. So again, this one was not given to us. So you are responsible for knowing the names and symbols of the first 36 elements. You don't have to know what order they come in, but if I say Br, you should know that that's bromine by the time the first exam comes around, not necessarily today. So first 36, as you see, this periodic table doesn't have symbols, so if we gave you the name bromine, you should be able to identify that as Br. It's not really going to be a specific test question, but if we identify an element by name, you have to know what its symbol is if it's in those first 36. So just a little bit of warning about that. All right, so we find Br here, and the number that's right above Br, I can zoom in a little bit more on that, is 35, okay? So 35 is the atomic number for bromine. That's how many protons every atom of bromine would have. Okay, so that comes from the periodic table, 35 protons, atomic number. And if this is a negative ion, if it just says minus, that means -1. We don't always write the -1 explicitly, but a negative charge there means there's one extra electron. So if it has 35 protons, to have a negative charge, it has to have 36 electrons. So that's the first part of this. We've identified the number of electrons in Br-. Now what we're looking for is a 2+ ion, a positive ion with a +2 charge that has those same number of electrons. So for that, what we have to do is sort of work backwards. If we have the same number of electrons in the 2+ ion, also 36, how many protons should we then have? 38, because we need 2 extra protons to have a +2 charge. So if our +2 ion has 36 electrons, it has to have 38 protons to have a net +2 charge. So we use the number of protons to then identify what that element is. So if we go to back to our periodic table, we know that the atomic number has to be 38 for that element. They're all in order, so that's easy to find. 38 is here, Sr, which you don't need to know, but that's called strontium, because that's beyond 36, so we won't ask you name and symbol for that one. But it's called strontium, and the symbol, which you can find easily, is Sr. So the 2+ ion that has the same number of electrons would be Sr2+. Okay? This one has 38 protons, 36 electrons. Both of these have the same number of electrons, but the different numbers of protons allow this one to be +2 instead. All right, any questions on ions? All right, so that, believe it or not, you guys might think we're going fast, but that's sort of on purpose. We're actually done with chapter 1 in the book. Chapter 1 is pretty short and not too complicated, I hope, as we saw, but if you have any last questions on it, yeah?
Wouldn't strontium 2+ have 40?
It would have 40 electrons if it was 2-. So remember that if it has a plus charge, it has to have more protons than electrons. So only if it was a negative charge would it have extra electrons. Got it? Okay. Anything else? All right. So we're done with chapter 1. I do chapter 1 a little bit quickly on purpose because there's not many topics. It's not terribly complicated, and chapter 2 is, just to warn you, a lot more dense. So we're going to spend more time on that one. There's a lot of topics. Some of the concepts in chapter 2 are a little bit tricky too, so we have to make sure we give enough time to them. So you should be all ready for really the first 2 homework assignments, because you have the review chapter that's due this week, and then next week is chapter 1, so you have plenty of time to stay caught up on that. I want to avoid getting behind at the beginning, because sometimes with how dense chapter 2 is, it's easy to fall behind at the beginning, and that makes it harder for you guys to get your homework assignments done in a timely fashion. So I want to avoid that. So we are going to move on to chapter 2 now, which starts with this idea called quantum theory. Now, quantum theory is conceptually excessively complicated, so obviously in a general chemistry class we can't go really too much into the weeds with it. But what we have to start with is talking about electromagnetic waves. And the reason for this is, as we'll see later on in this chapter, quantum theory is what allows us to accurately and in a meaningful way describe how the electrons are arranged in an atom. So at this point we know that there's a dense nucleus, we know that there's electrons sort of floating around that, but how exactly are those electrons behaving? How are they arranged? Are they in, what are their relative energy levels? How are they moving around, or how, what region of space they take up? All that stuff, which is very important in chemistry as it turns out, we don't have any insight into yet. And it really is quantum theory that gives that information in the most accurate and most useful way. But we'll work up to that gradually. But to understand quantum theory and some of the origins of it, we have to talk about electromagnetic waves, because many of the key experiments that were done, some of which we'll talk about in this class, the way that they sort of figured these things out about how electrons behave in atoms is by looking at the interactions of electromagnetic waves with materials, with different substances, atoms, molecules, metal surfaces, and so on. And so those interactions between electromagnetic waves and substances gave a lot of these key ideas. We have to introduce that first. So there's another name for electromagnetic wave is electromagnetic radiation. You may hear that terminology as well. And at a basic level, it's going to be energy that's propagated, meaning that it moves through space, by electric and magnetic fields. So electromagnetic has the words electric and magnetic in it. And these electric and magnetic fields, they oscillate in intensity as they travel. So if you had an electromagnetic wave traveling in front of your face, and you could somehow visualize the size of the electromagnetic field that wave has, it's going to go up and down as it passes in front of you. So it'll be up and down and up and down. That's what we mean by oscillate. Okay, so that's an electromagnetic wave. And so this picture down here kind of illustrates that. You have, in this diagram here, the blue wave represents the electric field, which, as you go through space or through time, oscillates up and down. And then you have a perpendicular magnetic field, that's what B represents as a magnetic field, shown in red, that oscillates with the same phase as that. The reality is that you don't necessarily need to always draw these sort of complicated diagrams that show the oscillations in both directions. We'll usually just draw waves as sort of simple two-dimensional waves. We'll, of course, assume and infer that the other wave is there perpendicular to that. It's not really two waves, it's the same wave, but they have two perpendicular components. But we just really can draw it more simply, as we'll see later on. So that's kind of what a full electromagnetic wave looks like, with the electric field component and the magnetic field component perpendicular to each other. Now, electromagnetic radiation are things that you have certainly encountered in your everyday life. So, visible light. All of the colors that you see from all the objects in the world or coming off of this screen, all of those are produced by electromagnetic radiation. If you have been in a medical situation or at the airport, they use X-rays sometimes, and X-rays are a form of electromagnetic radiation. Nobody listens to the radio anymore. I guess I'll admit how old I am and say that I do, but radio waves are a form of electromagnetic radiation, and microwaves, if you cook your food with microwave, that's a form of electromagnetic radiation. So there's all these different types of electromagnetic radiation. We'll define them more clearly in a little bit, but they are everywhere in our everyday life, even though we can't always, except for the visible light, we can't really see them, but they are there and they are important. Okay, so let's talk about then the properties of a wave. So when you have an electromagnetic wave, what are some of the ways that we can characterize it quantitatively? So I've drawn a wave here, and as I said, we'll usually just indicate these two-dimensionally. There is the perpendicular component as well, but we don't have to always draw that. It just gets too complicated. So there's two key properties of a wave that we need to know at this point. So one is called the frequency, which is abbreviated with the Greek letter nu. New kind of looks like the letter V, but just imagine that there's like a hurricane force wind blowing on the side of it, so it's kind of like a V that's tilted a little bit. It's a Greek letter, but it looks a lot like the letter V. So frequency can be defined as the number of cycles per second. And the unit for that is called hertz. So 1 cycle per second is 1 hertz. Hz is the abbreviation. So as an example, when we draw a wave like this in this diagram here, I didn't really label the axes at all. The horizontal axis in a wave diagram like this could be either time or length. So if we assume that we're talking about a unit of time here, let's say that this peak to that peak there is a time of 1 second. I'm being arbitrary here, but let's say this is 1 second time. And so in this 1 second, this wave goes 1 full cycle, top to bottom, back to top, 2 full cycles, 3 full cycles, 4 full cycles. So in that 1 second of time, this wave underwent 4 cycles. So the frequency of this, if that's 1 second, would be 4 hertz, which can be written as either inverse seconds or more commonly as Hz, as we said. All right, so that's 4 inverse seconds or 4 hertz. This would be the frequency of this wave if we said that that amount of time was 1 second. So the way to think about frequency is, again, imagine that you're standing still and you're watching a wave go in front of your face, and you can see the oscillation of that wave in time as it goes through. In reality, you can't, but let's say you could. So if the number of times that it oscillates up and down in 1 second is the frequency. So if you have a really low frequency, the wave would be like oscillating slowly like this. People on YouTube are not going to have any idea what gyrations and motions I'm making, but sorry about that. So anyway, the oscillations, if they're slow, that would be a low frequency. If you have a higher frequency, they're going to oscillate really fast as the wave travels in front of your face. So that's what frequency means, how many oscillations per second. Now the other key parameter, let's then instead, we're going to do it on the same diagram, so I hope it doesn't get confusing, but let's instead assume that this horizontal axis, instead of being a unit of time, is a unit of distance, length, okay? So the other one would be what's called wavelength, which is abbreviated with another Greek letter, lambda. As a bonus of taking chemistry, you also get to learn the Greek alphabet. So wavelength is abbreviated with lambda. And so if you have a wave where you're defining it in length dimensions, or a way to imagine this is, let's say we could take an electromagnetic wave and freeze it in space. So in reality, they're traveling through space all the time. But let's say we could freeze it in place and measure the distance from one part of the wave to another. The wavelength is going to be the distance between equivalent points on a wave. So if we were able to freeze a wave in space, which we can't really do physically, but imagine that we could, if we measure the distance between equivalent points on that wave, that would be the wavelength. So in this diagram here, if this is distance units instead, we could go from one peak to the next peak. That distance would be one wavelength. But you don't have to necessarily measure it peak to peak. You could also measure it from the valley to the valley, or the bottom of each wave. So if it's any two equivalent points on the wave, two consecutive equivalent points, that would be defined as lambda. Or even here we have, this is sort of what you might call the node of this wave. So as you're coming on the downslope here, one full cycle later it would be over there. That distance is also lambda. So you can define it in a lot of different ways, but it's just the distance between two equivalent points on the wave if you were able to freeze the wave in space. We'll get some idea of how big these wavelengths are, and actually they can vary by quite a large amount. So the light that you can see with your eyes is usually a wavelength of on the order of like 10 to the minus 7 meters, like 400 to 700 nanometers, which is actually really small. You wouldn't be able to measure that distance very easily. But then radio waves, the ones that travel through everywhere and carry sound to your devices, those can have wavelengths that are on the order of like a meter or so. So if you had a radio wave going through this room, which I'm sure we have many at this point, and you could actually like freeze it in space and take a picture of it, the wavelength of that would be like on the order of this big. So they can vary by quite a large length scale depending on the type of electromagnetic radiation you have. But you have frequency here and you have wavelength, are the two key parameters of an electromagnetic wave that we need to know. All right, so that's going to be the two things. Now, what we also want to start talking about a little bit is going to be the relationship between those two, the relationship between frequency and wavelength. So what I have here are two different waves now drawn on the same diagram, one in blue, one in red. Hopefully you can all see that okay. All right, so if we want to measure, if we look at the two wavelengths and frequencies of these here, let's talk about wavelengths first. That's a little bit easier to deal with. So if we look at the blue wave here, which I'll call A, okay, if we go from one peak of the blue wave to the next peak there, that's going to measure the wavelength. And it comes through okay on the screen, so you should be able to see it. I have a little horizontal scale here. So how many units over is that? That's 1, 2, 3, 4, 5, 6, 7, 8. So whatever this horizontal scale is, we have 8 of those for the wavelength of A. Okay, there are 8 units between the peaks of A. If we go to wave B, which is the red one, let's measure it over here so we're not overlapping too much. If we measure that wavelength for B there, peak to peak is the easiest way to do it, what we count is 1, 2, 3, 4. So the wavelength of B on this diagram would be 4 instead of 8. Again, whatever units that is not specified here. And then if we instead assume that this is plotted in time units and want to look at the frequency, let's look how many cycles these waves go from here to here. All right. So we'll go through the same period of time, see how many cycles each wave undergoes. And so for wave A, the frequency would be, here we have how many oscillations does wave A do in that time. We're starting at a peak, so we go 1 and we go 2. So we did 2 full cycles of the blue wave, so the frequency would be 2. And then for wave B, in the same period of time, starting here and ending here, same place, here and here as I've drawn it down here, for wave B we have 1, 2, 3, 4 cycles. So the frequency for B in this diagram would be 4. So what you might notice from this very crude and very simple description of this is that the wavelength of A is 2 times the wavelength of B. A is 8, B is 4, but the frequency of wave A is only 1/2 that of wave B. So there's what's called an inverse relationship between them. Wavelength A has a larger frequency, but a larger wavelength, but a smaller frequency. Wavelength B has a smaller wavelength and a larger frequency. So those two are inversely related to each other. If the wavelength is higher, the frequency is lower, and vice versa. So we call that an inverse relationship. So that's how those two are related to each other. And so that allows us to derive a pretty simple equation between wavelength and frequency. So when you have an inverse relationship, meaning again, that means that the wavelength is bigger, the frequency is smaller, or vice versa, you can write that in this way. The wavelength lambda is proportional to 1 divided by the frequency. So whenever you have an inverse relationship, that's what that means mathematically. Okay? Now, if we want to get rid of this proportionality sign and make this an equation with an equal sign, the way that you do that in math is you put a constant on one side of this equation. To make an equation, you put a constant on one side. So we could put it on either side in principle, but the way that it's conventionally defined is to put a constant c over here, and then we can rearrange the equation by cross-multiplying to write it in the more familiar form of nu times lambda, frequency times wavelength, equals c, a constant. And in this equation, c has a very specific definition. That's the speed of light. So that's how wavelength and frequency of any electromagnetic radiation are related to one another. The product of the two equals the speed of light, c. That number is given on your periodic tables. You don't have to memorize it. We have a series of constants on your periodic table, and c is one of them that's there, so you don't have to worry about memorizing it. But it's 3.00 times 10 to the 8th meters per second. Exceptionally fast, as you probably know. That would be the speed of light in a vacuum. In regular atmosphere or in liquids, in undersea, the speed differs a little bit, but That's the number that we'll always use in this class, 3 times 10 to the 8th meters per second. And the other important thing about wavelength and frequency then is that they kind of define then the type of electromagnetic radiation that you have. So we talked about already several different types of electromagnetic radiation, X-rays, microwaves, visible light, and so on. And those are all defined from each other based on the different frequencies or wavelengths that they all have. Okay, so what you have here is, we don't have to know the numbers necessarily how they're divided, but you should know a little bit about the order. So this is ordered from high frequency on the left here. So this is high frequency, and this is low frequency on the right, or this is low wavelength or small wavelength on the left, and long wavelength or high wavelength on the right. Again, they're inversely related to each other. So that's how this scale is oriented, and this is the order that they come in, and they're all things that you should be familiar with. So the longest wavelength and lowest frequency is radio. Microwave is after that. Infrared comes right below the visible, and then again, the visible range, that's the part that we can see, is actually a really small slice of the electromagnetic spectrum, and it goes from 400 to about 750 nanometers. If you can't see that, that's 400 nanometers, that's 750 nanometers, and that's the small range that we can actually see with our eyes, at least that humans can see. Some other organisms are a little bit different than that, but it's all pretty close to that. And then above the visible in terms of frequency, or with smaller wavelength, is UV, ultraviolet, then X-ray, then gamma ray. So basically there's 3 that are below visible, 3 that are above in terms of frequency, and you should have some idea about the order of those. You don't need to memorize the numbers, but the ordering of them is something that could come up. Okay, so that's how we characterize electromagnetic radiation. So let's finish then with a few sample problems about waves, just to see the types of things that you'll have to do. Again, we're not going to get through everything today, so we'll just pick it up next time, but we'll do a few sample problems to, or at least one sample problem to wrap this up, and maybe one other quick concept if we have time. All right, so here we have orange light. It kind of looks maybe more red on some screens, but it's kind of a red-orange color, and it has a wavelength of 600 nanometers. We want to know what is the frequency. So anytime we have a problem that asks us about frequency or wavelength of electromagnetic radiation, we automatically should think about the simple equation that we just introduced, which is that the product of the two equals C. But this is probably the first type of problem in this course where we have to be very careful with our units. We always have to be careful with units, but here's really the first one where it can especially be a problem if we're not judicious about that. So we're looking for frequency, so we can do some quick algebra and say that frequency nu is equal to C divided by lambda. We just divide both sides by lambda. And so we know that C is a constant. It's on our periodic table. I didn't give it to you here, but it's not a number you'd have to memorize, and it's always the same for any problem that uses it. 3 times 10 to the 8th meters per second. We're going to divide that by the wavelength, but we notice that the wavelength is given to us in nanometers. So if we're going to divide two numbers, they have to be in the same unit first for the length unit to cancel out. So if this is in meters per second, we need to convert this number to meters first before we divide the two. So we can't forget to do that. So we have to convert the wavelength lambda into meters before we can proceed. So it's given to us as 600.0 nanometers, and then we have to know the prefix nano, what that refers to. So this is part of the review chapter, and I reproduced the table here in case you don't have it, but you should all have access to the book. I don't know if the number of this table changed because it might be an older version, but nonetheless, these are the units that you have to know. Some of these are more common than others. Ones in blue you should definitely know. The ones in black probably not going to come up. But anyway, we see that nano here, nano is 10 to the minus 9, okay? So 1 nanometer is 10 to the minus 9 meters, so there's actually two ways of writing that in terms of conversions. So what we want is we want nanometers to cancel out, and we want meters to be the unit that we get into. So we have to put nanometers in the bottom. There's two ways of writing this. You could either write it as 10 to the minus 9 meters is 1 nanometer. That's kind of how the unit is defined. I don't particularly like doing negative exponents in my calculator, so my preference and the way that I'll usually do it is to write it as 1 meter is 10 to the 9th nanometers. They're mathematically equivalent, it just avoids negative exponents. Whatever you prefer is fine, but you have to convert them correctly to divide out nanometers and get into the correct units of meters, which is 6.0 times 10 to the minus 7 meters. All right, so make sure you know these prefixes down here in that table or whatever, that could come up from time to time as part of the review chapter. So now we're ready to put this in. We have it in the correct units, 6.000 times 10 to the minus 7 meters. Meters divide out, and that leaves us with 5.000 times 10 to the 14th hertz. And in most cases, this is how we would ask you to format your answer, or we would tell you in Blackboard how to do it. There are some, you could write this as 500 terahertz as well. We won't usually deal with those sort of big prefixes like tera, but that would be equivalent if you want to write it in a more convenient form. But either way, we didn't really specify in this problem. That's how you would do it. It's just using that simple equation, nu times lambda equals c. All right. All right, the last thing that I'll cover today, it's going to be a little bit disjointing, so I'll have to pick it up next time, is the idea of the quantization of energy. So when people first started learning about electromagnetic radiation, they sort of assumed that you could have any energy value possible. So electromagnetic radiation carries energy, as we know, and the assumption was that, again, it's continuous, just like they kind of thought for charge initially. They thought it was a sort of a continuous value. You could have any value of energy that you wanted to from electromagnetic radiation. But there were some experiments that were done that kind of worked against this. And we're not going to go through all the details of them, but let's talk about this one here first, black body radiation. So the concept here is that if you take a solid and heat it to very high temperature, if you have an electric stove, you've probably seen this before, or if you do wood burning or things like that. If you heat a solid to very high temperature, which usually means around 1,000 Kelvin or more, it will emit visible light. This is how incandescent light bulbs work, although we don't use those as much anymore. We're all in LEDs now, but you've probably seen this in some context before. And that's called black body radiation. So the problem is, people started making measurements on black body radiation. What is the frequency of the light that's given off, and how, what's the distribution of frequencies? It's not just one value. And if you just use classical physics, what was known at the time about energy and electromagnetic radiation, it assumes or says that matter can absorb or emit any quantity of energy. So with that assumption, they kind of came up with what they thought black body radiation should look like in terms of its wavelength or frequency profile. But to make a long story short, if you make that assumption using classical physics, it fails to explain the wavelength and intensity relationship of black body radiation. And what they originally called this was the ultraviolet catastrophe. I think they were being a little bit dramatic about it, but basically the idea was that if you measure the wavelength, all the different wavelengths that make up black body radiation and how intense they are at each wavelength, you should get a certain profile. And classical physics predicted that as you go to the ultraviolet range, to shorter and shorter wavelengths, the intensity would increase and increase and increase and increase. In reality, that didn't happen. It was more like a bell curve almost. And so that caused a problem because the shape of that curve didn't match the theory that they had at the time. And anytime the theory doesn't match the data, that means that there's something wrong with the theory. That's the scientific method. So the solution to this, which we will talk about more next time, came from Max Planck. And the idea then is that energy is quantized. So you can't have any continuous value of energy coming off of a solid. It's quantized in whole number multiples of a new constant h times the frequency. So you can almost think of, or getting to the point where you can almost think of electromagnetic radiation in the same sense as atoms. You can't have a partial piece of electromagnetic radiation. You have one piece that has energy of h times frequency, second piece has h times frequency, but you can't have partial pieces of that. Okay? And so what that means is that the change in energy for this solid as it undergoes black-body radiation is some whole number n times h times the frequency, where h is an exceptionally small constant, 6.626 times 10 to the minus 34 joule a second. This one is also on your periodic table, so you don't need to memorize it, but you probably will, whether you want to or not. And this is called Planck's constant. And n here is an integer value, 1, 2, 3, and so on. So the amount of energy that you can get from electromagnetic radiation is always some whole number multiple times h times frequency. It can't be a fractional multiple of that. So that was the first idea, that this energy, so matter is quantized in the form of atoms, and matter is made up of little discrete pieces called atoms. And this was the first experiment to introduce the idea that energy is also quantized in terms of little discrete units of energy. So we'll talk more about that next time and get into how this relates to chemistry. So enjoy your weekend, and I'll see you guys next Tuesday.